We're now starting part 2 of the book, which is on matrices. The first part was on vectors. The third part will be on least squares. These are the components of the subtitle of the book. Okay, so now we're going to talk about matrices, and we'll start with just the basic notation and nomenclature first. Okay, so a matrix it's a rectangular array of numbers written between square brackets. Now, some people also use curved brackets. So that's a variation that you will see sometimes. So this is what a matrix is. It's a square array, and we talk about its size or its dimensions. And its dimensions are given by the number of rows, by the number of columns. So for example, this matrix right here has 3 rows and 4 columns, so we call that matrix a 3x4 matrix. So that's how you would refer to this. It's a 3x4 matrix. Now the entries of a matrix, these are the numbers inside inside the array. These are called entries, coefficients, or elements of the matrix, right? And you refer to them by their row and column index. So the row index is 1 for this row, the top row of numbers. It's 2 here, and it's like 3 here. And the column index is like 1 here, 2, 3, 4, that kind of thing. That's how that works. Oh, I should mention that the indexes start at 1. That's an important distinction because in some computer languages, indexes start at 0. But in standard mathematical notation, indexes for matrices, for vectors and matrices, they're indexed starting from 1. That's something to remember. Okay, so if we refer to this matrix up here as B, then Bij refers to the ij element. I is almost always reserved for row and j for column, but that's just that's just a convention. And you'd say that Bij. So for example, in this matrix, if this is B, then I could ask, what is B2, 3? Well, let's take a look. The 2 that's the row index, okay? And the second is the column index. So we go to the second column and the third row, and we get this number right here. And so this is minus 0.1. There you go. So that is the, you'd call that the 2, 3 entry of B is minus 0.01. Okay. Now, like vectors, we have equality between matrices, and we overload the symbol. So there's no special symbol for saying 2 matrices are equal. It's the same old equals. And here's what it means for 2 matrices to be equal. First of all, number 1, they must have the same size. That's the first part. And second of all, the corresponding entries must be the same, right? So just like a vector. Okay, now matrices are classified according to their shapes. If you have an m by n matrix A, and that means that if A has, if here's A, it means that it's got m rows and n columns. So this is A, our matrix. I haven't written out the entries, but I'm just showing you the size, the number of rows and columns. Okay, now the matrix is called tall if it has more rows than columns, and it's kind of obvious why. It means that if the entries were took a constant width, then it would actually be physically a taller. The symbol, the way we describe the matrix, write it down, would be taller. It's wide if there are more columns than there are rows. And it's square if there's an equal number of columns and rows. So I think these are pretty well standard standard terms. Anybody in math or applied math or any associated field like that would understand these terms. So you have square, tall, and wide. Now, in fact, vectors are actually special cases of matrices. So let's see how that comes about. So we're going to consider an n by 1 matrix to be an n vector. So and vice versa. So if I show you an n vector, you can think of it as an n by 1 matrix. N by 1 matrix means it simply has a single column. That's all. So for example, if I write 2 minus 1 like that, and you say, what's that? You could say, well, it's a 2 vector. It is. It's also a 2 by 1 matrix because it's got 2 rows and 1 column. Okay, so And we'll see that that's not going to cause any harm. We'll talk about that later. Okay. Now, even more extreme is a one-by-one matrix we consider to be just a number. It's the same as a one vector is just a number. We don't distinguish. So we don't really distinguish, for example, between this, right? The one vector with sole entry -3 and the number -3. We don't distinguish. Okay. Now, you might ask, what is a 1 by n matrix? So that's a super interesting thing. It looks like this, right? So I have square brackets and I have the numbers, but they're in a row, not a column, right? So this is a column vector. And by the way, we also write it, the alternative notation is with commas, right? Right, something like this, okay? And so in this book and course, we're going to be very, very, very strict about notation, right? So, that's a column vector. You can write it this way or you can write it that way. This is a row vector. There are no commas, there are no semicolons or anything like that. That's what it is. You can't put commas in here and say, oh, well, gee, why, we're going to be very strict about notation. Having said that, I should say, I'll give you another warning, is that I very much hope that you are following along the material in this class, programming or just fiddling around in some computer language. Could be Julia, could be Python, could be MATLAB, well, it could be a lot of different things, right? You should be aware that in all of these languages, there's a computer syntax for writing matrices, and it's not exactly this. So just be aware that you'll have to unfortunately keep two notation systems in your mind. If you work with one computer language, I mean, honestly, if you work with two computers, you have to take more. It's like whatever, speaking French and German. You have to keep the mathematical notation in mind, and you have to keep the computer notation in mind. And you have to have a little table that translates between here's how you express a column vector and a matrix and a row vector. One very important thing is don't ever confuse these two notations, right? So if you're doing or writing math, write math. If you're programming, don't write math. Besides, your compiler or parser is not going to accept it, okay? But just be aware that there are two syntaxes. I'm showing you here the standard mathematical syntax, okay? So please keep them separate. One other thing I should say is that, people, once you know a lot and you get familiar with all these things, people do actually kind of don't distinguish between row and column vectors, okay? I'm going to just go ahead and say this. That's bad, okay, to not do that. But nevertheless, a lot of people do that. Once you kind of know your way around. For now, and certainly for the entirety of this course and this book, we will not be casual like that. This vector, this thing, is not the same as that. This thing is a 4 vector, period. If someone says column or row vector, you'd say it's a column vector, but the default for a vector is a column vector. This is a row vector, and it's not the same as a column vector. Like, for example, if I asked you, is this equal to that? The answer would be no. And actually, or it would be some worse thing, like, hey, what are you doing? You cannot ask me if a 1x4 matrix is equal to a 4x1 matrix. Doesn't even make sense, right? So it could be instead of no, it could be some kind of nasty comment coming back like, hey, you can't even, they're incomparable, something like that. Okay. All right, so I just mentioned that here. Okay, now if you have a matrix, we can actually talk about its columns and its rows. And these are kind of obvious concepts, but let's and this is very simple, but we're going to see it's going to be very powerful ideas come from this. Okay, so now suppose I have an m by n matrix, and the entries are going to be capital A, I, J, and that's for I going from 1 to m, they're m rows, J going from 1 to n because it's n columns. So the jth column of it is this, and what that means is I'm going to give you all the rows, so you can see A1 down to AM. That's the first index, the row index. And the second index is always J because it refers to the column. And so the jth column is this, that's an M vector because it gives you all the entries in that column. The ith row is a row vector, and it's an n row vector, and it's all the entries in the ith row. And so you can see here every one of these the first index, the row index, is always I, and the second one goes from 1 to n, which is the width of the matrix. Okay, so that's a row vector. Now another concept that comes up is a slice. And that's actually one of these concepts that actually originated in computer languages and then made its way back into mathematics. Okay, so and that's fine because they kind of go back and forth like that. So here, the colon notation p colon q means the integers q, q plus 1, q plus 2, dot, 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 up to q. Okay, so that's what that means. So it's an index range. I should add, in programming languages, you have more sophisticated things. Like you can say p colon 2 colon q in a computer language, and that means it means p plus 2, p plus 4, and so on. So the second one is called the stride, and then until you get to q or less than q or something like that. Okay, that's this we don't use. So that's computer notation. But this we do use so if this says please take between the p and q rows and the r to s columns, and so what you get is exactly that. That's a submatrix of A is what it's called. We'll get to that in a minute. A submatrix. Well, we'll get to that. Okay. Now block matrices, this is like block vectors. You can assemble matrices together to make a bigger matrix. Or another way to say it is you can have a matrix whose entries are matrices. That's a very interesting interpretation of it. So let's see what that means. Here's a matrix A equals B, C, D, E. Now, if B, C, D, E were numbers, you would say, well, that's a 2 by 2 matrix. It is. So what we do is we call these this is a block. These are block matrices, and we're going to call these submatrices, or even literally, you can even say the submatrix entries of A. Now, there's some rules here, right? That if you look at a row, this is a block row, BC. Now, for them they have to have the same height, otherwise they can't go together. And that means they have to have the same height, which is the number of rows, right? So B and C have to have the same number of rows. In addition, like a column, here's a column, C stacked on top of E. They have to have the same width, and that means they have to have the same number of columns, C and E. So that's the rule. So let's do an example. Here's B, C, D, and E, and a couple of things to mention is, if you like, you could call B a row vector or a 1 by 3 matrix. C, you could simply call the number -1, or you could call it a -1 vector, or the -1 1 by 1 matrix, your choice. And here's D, that's a 2 by 3 matrix, and E is a 2 vector, or if you like, a 2 by 1 matrix, right? So, okay, so we're going to form this block matrix, BC, DE, and let's first check that the rules work. So the height of B here is 1, right? So you can see that here. The height of C is 1, so we're good on the top row. Bottom row, D, E. D, the height of D has 2 rows, and E has 2 rows also. So the second row has been audited from the dimension point of view. Now let's take the first column. That's B stacked on top of D, and so B is 3 wide. It has 3 columns, B. Columns are silly, they're just numbers, but it's got 3 columns, B. That's stacked on top of D, and sure enough, D has got 3 columns, so that's cool. And then the final one is C stacked on top of E. C has 1 column, E does 2. We're cool. Okay, and it's a big drum roll. It's not very exciting. This is the matrix obtained with these block matrices, right? So, so that's the idea. And I could even here. I'll even try to do this right. And let's see. I think I got it right. There we go. Okay. So I've partitioned it there. By the way, sometimes when you have a block matrix, people will actually draw a little dotted or dashed line inside the matrix to show you the submatrices that they want to show you. So here you can see there's B, C, D, and E, and everything is cool. Okay, so all languages for manipulating matrices have methods for constructing block matrices. And by the way, and sort of the converse of that is to extract a submatrix, and so that's slicing. All computer languages and packages for manipulating matrices will also have a mechanism and syntax for computing, for extracting slices or submatrices of matrices. Okay. Now, if you have a matrix, it's m by n. We can actually write it as a block matrix where the blocks are actually just the columns. So we can, and this we'll do many, many times. So A is, when I write it this way, notice that it looks like if the A1 through AN were numbers, that would be an n row vector. But here, they're actually columns. Oh, also I should say that this matrix A could very well be tall, but visually, when you write it down this way, it looks wide, but that's another story. Okay, so here, so A1 here is the first column, and they're m vectors because the height of A is, it's m by n. That means it has m rows. So each of these is an m vector, A1, A2, A. And in fact, a matrix is often sometimes it's just thought of as a sequence of vectors of the same size, of course, right? So, and that's a very common use of a matrix. It's literally just to store a sequence of vectors. We'll see examples shortly. All right. Now I can also take a matrix and I can decompose it as a block. This time I'm going to make them the rows. So here are the rows, and I'm going to call them B1 through Bm. Now these are row vectors. So B1 has a dimension which is 1 by n. So these are these are n row vectors, the B's. Okay? And we'll see several times, it's surprising, but simply going back to this interpretation of what a matrix is actually going to be quite useful in a lot of applications. We're going to see that. Okay, so let me just quickly give you some examples. You're going to see a whole lot more before the book is over, but just to give you a rough idea of where the matrices come up. Here's a natural one, is in an image. An image, of course, is chopped up into pixels, and so here, here's your image, and now this is a bit silly, but here's something which has 2 by 3 pixels. Now that's ridiculous because most images are, hundreds of pixels vertical by hundreds horizontal or thousands these days, right? So you would never have an image that has, that has 6 pixels. Doesn't make any sense. Well, but technically this is what it looks like. And then what you're doing here is you're simply giving the value in here. This is a grayscale or monochrome image, and so what that means is it might go from 0 to 1, or a very common scaling now for historical reasons is 0 to 255. So, okay. Anyway, so that's the idea, is a matrix could represent an image, a monochrome image. Here's one from data. Aij could be the rainfall in location I on day j. That's it. So I'm interested in 10 locations and let's say a year, so 365 days. Then I would have a matrix which is 10 by 365, and that would give me the rainfall at my 10 locations. So it's going to have a height of 10 and a width of 365. So it's going to give me 1 year of rainfall data at 10 locations. And now what's interesting is whenever you see a matrix like this in some practical, you should ask yourself, immediately, what do the rows and columns mean? And it's not a big deal, but it just means you should be thinking about it. So let's see what this means in this case. So let's talk about a column. Let's look at the 17th column of this matrix A, the rainfall matrix. What does it mean? Well, the column indexes days in a year. If the first one is January 1st, then this is going to be January 17th. So the 17th column of this matrix, of this rainfall matrix, is a 10 vector, and what it does is it gives you the rainfall in my 10 locations on January 17th. That's it. So you might even call it it's actually the rainfall in my 10 locations on a certain date. Okay, let's look at the third row of this matrix. Well, that's a that's a 365 row vector, okay? And the third row, the meaning of that is it's the third location. Let's say that's Palo Alto. So it's Palo Alto. And then you get the row gives you the 1 year's worth of rainfall. Okay, so that's what it means. So a row vector, a row of this matrix you can interpret as a time series of rainfall at a particular location. Which location? Depends on the row. So that's the idea. In Palo Alto, there'd be a lot of zeros in that. Okay, not so much in a rainforest, but in Palo Alto, that would be a sparse matrix. Okay, here's a very common one is multiple asset returns. So here I have a set of assets. In fact, the slang for that, we'll talk about this later, is called a universe of assets, right? So I would have, let's say, n assets or something like that. And these could be stocks that you're going to invest in, or the stocks that you might invest, something like that. And then we'd also have periods, days. So this could be, I could index a period, which could be trading days, right? Which are like typically Monday to Friday, something like that, not counting holidays, right? So you get about 250 in a year, but that's the idea. So there, if I asked you for this matrix, what is the meaning of a column? It's super interesting. Here, columns are indexing, the columns are indexing the assets, and the row is indexing the time period or day. For example, if we make it a day, it doesn't have to be a day. So, for example, the third column of the matrix R is the time series of the return for the third asset. Very interesting. You could plot it. It would make sense. You could look at it, all sorts of stuff. Okay. Let's talk about rows. What is the fourth row of the matrix R? Well, the fourth row means that I is 4 throughout that row. And that means it's on the fourth trading day. It gives me the returns of my entire universe. That would be the slang of stocks, right? And it means that for all n stocks, I give you the return, right? So that row might look like this. Let's make it minus 0.02, 0.03, right? And so on. And what this would mean is the first asset on that period had a negative 2% return. The second asset, that's here, had a plus 3% positive return, and so on. That's the idea. Okay. All right. Here's a very common one, and it comes up in data science, statistics, machine learning, and it's this. It's a feature matrix, also just known as a data matrix, and we'll say a little bit more about that, and you'll see a whole lot of this later in the class. So here the idea is you use a matrix to store the value of a bunch of features for a whole bunch of entities. Entities have other names like samples, examples, or in specific contexts, it could be, a purchase or a customer or a student or something like that. So, but in general, it's just an entity. And so here, xij is the value of feature I for entity j. So in this case, all you're doing is you're thinking of the matrix in terms of its columns like this, and it would go like that, okay? And these would be m, that's m, these would be m vectors, and x1 is the feature vector for item 1, x2 is the feature vector for item 2, and so on. All of that is shoved together in what's called a feature matrix or a data matrix. So that's the idea. That's what this looks like. Okay. Again, I'll just show you some simple examples, and then we're going to see a whole lot more later. So a graph or relation actually can be encoded as a matrix, and that's often useful. So a relation is, let me tell you what a relation is. I have a finite number of objects. I'm going to call them 1, 2, 3, up to n. By the way, they could have other names, like CEO, CIO, head of sales, I don't know, this kind of stuff. Okay, so they don't, but we're just going to call them 1, 2, 3, up to n. Okay, and a relation is a set of ordered pairs among them. Okay, so for example, This is you'll recognize that squiggly bracket as defining a set, and the entries of a set are given between the brackets with comma between them. So that's an entry of the set. That's the second entry, third. Oh, I should mention sets don't have an order. So I shouldn't have said the second entry. Well, the second entry in our description of the set, but a set doesn't have an order to its entries, to its elements. So here, and the entries are themselves pairs. So here it's 1, 2, 1, 3, 2, 1. Okay, and that's what that looks like. And you know, we can you know, this could be an asymmetric social network graph where 1, 2 means 1 likes 2. There. 1, 3 means 1 also likes 3. 2, 1 means, well, 2 likes 1. Okay, so it's mutual. That's good. Okay, and you get the idea. So this is a type of thing a relation would encode. Okay, these could be, for example, a bunch of web pages, and the objects could be web pages, and this could say that web page, let's say 2, links to web page 1. That's what it means. It means that it's a link to. Okay, for example, that's for example. Okay, now a lot of times people will write a relation or visualize it as a directed graph, and a graph. If you haven't seen this before, I hope you'll see it again in other classes, but maybe you haven't. But I'll be very informal here. But a graph, you think of the objects as these are called vertices or nodes. It's just it's vertices or nodes in a graph. Then the actual relations between here are denoted with an arrow. And so here what we're doing is we're drawing an arrow. So you draw an arrow. If you have here, let's look at 1. Here's something. It says 4, 1. And we're interpreting that to mean that there's an arrow from 1 to 4. Note it's kind of backwards. You might think it would be 4 to 1, but we're going to write it 1 to 4. By the way, people use both definitions of that. Okay, so every one of these blue arrows is one of these things here. And we could just do an audit. Let's find 3, 4. Well, that represents something, an arrow going from 4 to 3. And let's check it. Oh, it's right here. There you go. It's this one right here. Okay? That's that one. Okay, so this is the idea. Of course, this is very abstract now, but when any application, it's actually kind of it'll actually be kind of interesting to see. It'll be more clear what all this means. Okay, so the connection of matrices is this: we can write a graph or matrix. We can write a graph as a matrix. That's a very common way to describe it, whose entries are either 0 or 1. And what we do is we say Aij is 0 if Ij is in the relation, meaning if you have an edge from J to I in the graph, we put a 1 there. And so this relation and this graph and this matrix all describe the same relation or graph or matrix or whatever. So, and we can check here. Let's see what does that mean? Well, that's the 3, 4 entry, and so that corresponds to this element right here, and it's the same as this one, that edge. So this number, this edge, and that entry of the relation are all the same. They represent exactly the same thing. Let's check another one. How about the 0? That is the 4, 2 entry of the matrix A. So it's 0, and that means there is no edge from 2 to 4, right? Or it says that 4, 2, the pair 4, 2 does not appear in R, and you can look here and you will see indeed 4, 2 does not appear. Visually in the graph, it says that there is not an edge from 4 to 2. Let's see, did I get that right? From 2 to 4. I switched them around. And indeed, there is not an edge from 2 to 4. There is one from 4 to 2, but not 2 to 4. Okay, so this is just an example. So, matrix can also represent a graph or relation, and we'll see plenty of that in the sequel. All right, I'm going to mention some special matrices now. This is, not unlike the zero matrix, the zeros vector, the ones vector, the 0, 1, and the unit vectors, right? So there's some analogs of that in matrices, and we'll just get that out of the way right now. So if you have a matrix and all the entries are 0, it's written as 0, and sometimes you can put a subscript below it if you want to let somebody know what the size is, right? Otherwise, you just write it as 0. So same way we write 0 vector. So this is highly overloaded notation. It means that when you have 0, it either means it could be the 0 number, it could be the 0 vector, or it could be the 0 matrix. It's your job to find out which is meant. Okay, so that's kind of the idea. Okay, an identity matrix. That's something that you don't. There's no analog of that for vectors. Here's what it is. It's a matrix. It must be square, number one, and then its diagonal entries. That's the entries here where the row and column index are equal. They're 1, and the off-diagonal entries. Those are the entries where I is not equal to j are 0. So this is an identity matrix, an identity 2x2 matrix, and that's an identity 4x4 matrix, right? And this is also just written as I. That's pretty universal, actually, notation. So if you just walk into the math department and say I, okay, but you may have to say something about the context as matrices, and then there will be absolutely no, everyone will understand what you're talking about. Just the identity matrix. Okay. Now, like vectors, we have a concept of a sparse matrix, and a sparse matrix is one where a lot of entries are 0. We've already seen two. Here's the sparsest matrix there could possibly be, the 0 matrix, because all entries are 0. The identity is sparse because, only the diagonal out of n squared total entries, you only have n, which are non-zero. And the idea is like vectors. If you have a sparse matrix, they can be stored more efficiently, and they can be manipulated more efficiently. Now, we haven't actually seen anything you can do with matrices yet, but we're going to. And all of those operations can be done more efficiently when the matrix is sparse. Okay, so these are just some quick ideas of matrices. We have diagonal and triangular matrices, right? So again, these are not things you don't have no analog of this for vectors, right? So a diagonal matrix is a square matrix for which aij is 0 for I not equal to j, and that means simply that if your row and column index are different, the entry is 0, and so that's a diagonal matrix right there. Okay, that's an example. And you can see, here are the ones, this is referred to as the diagonal of the matrix. It's where I equals j. And then this is referred to, these entries are part of the off diagonal. And off diagonal just means I is not equal to j. Okay? So we have a notation. If you have diag of a1 through an, and these are numbers, then that's a diagonal matrix with those entries. So in that notation, diag of 0.2 minus 3, 1.2 would be this 3x3 matrix. Okay, so that's the diag thing. I should say that all computer languages for manipulating matrices have something that will affect this operator, diag. It allows you to construct a diagonal matrix. Lower triangular matrix means that aij is 0 if I is less than j. And so a lower triangular matrix is going to look like this, right? It's going to have it's going to have stuff on the diagonal and below, but everything above the diagonal is going to be 0. Okay, so it's going to look like that. Here's a lower triangular matrix right there. So that's lower triangular. Here's another lower triangular matrix, 0. I mean, fine, it's lower triangular. It's also upper triangular, by the way. Identity, right, is lower triangular and upper triangular. And in fact, we can say the following. If a matrix is lower triangular and upper triangular, it's diagonal. So that's sort of the idea behind this. So here's an upper triangular matrix as an example, and here's a lower triangular one. Okay, so yeah, by the way, not one bit of this should have any particular interest to you yet. Okay, so I'm just admitting that, right? That we're just talking about the nomenclature, the plumbing. We're going to talk about things like we'll see diagonal and triangular matrices going to play an important role. But for now, this is just you're just learning the basics of how you refer to matrices and things like that. Here's your first matrix operation. That's not true. We already had a couple. We had we can actually form blocks, so we know how to stack uh, matrices vertically and horizontally to create blocks. But here's our second one: is transpose. Very important concept. And what it is this: I have an m by n matrix A, and if I put this superscript with a t, by the way, not an accident. That's the same t that we use in the inner product. Not only that, if you will recall, when we were talking about inner products, I tried very hard but failed. And several times, instead of saying the inner product of A and B, I actually said A transpose B, which is what it is. But so the notation, I shouldn't have said it then because we had not yet had the concept of transpose. But now we have it. Henceforth, I can refer to the inner product as, well, we'll get to that, A transpose B. All right, so. But just to let you know, you've seen that notation before where it was completely mysterious and now it's not. And you know what the T is now in our notation for an inner product. It's the transpose. Okay, so it's this. The transpose just swaps the row and columns. That's all. It does nothing else. So here's an example. Here's a matrix. It's 3 by 2. Its entries are 0, 4, 7, 0, 3, 1. If we transpose it, you will see that, for example, the first column here, 0, 7, 3, becomes now the first row, 0, 7, 3. The second column, 4, 0, 1, becomes the second row, 4, 0, 1. Or, if you like, the first row over here becomes the first column, however you like. So all a transpose does is it swaps the rows and the columns, okay? Of course, if you transpose a column vector, you get a row vector, and vice versa, okay? One pretty obvious thing is A transpose transpose is A. So if I take a matrix, I transpose it a second time, I get back to the original matrix. Okay, so pretty straightforward. We also have addition, subtraction, and scalar multiplication of matrices. So just like vectors, that's not an accident, of course, because matrices generalize vectors, right? Because you can think of a vector as an n vector as an n by 1 matrix. So, okay. So, like vectors, I can add two matrices of the same size, and I do it just simply by adding I just add the corresponding entries. Subtraction is the same. Scalar multiplication is the same. I just do it entry by entry. And there's a whole lot of obvious properties. You should probably, make sure you understand these. You can't just write these down. Technically, somebody should show that these things hold, right? I mean, it's incredibly boring to do that, but nevertheless, at the same time, I don't know the right way to do this, but don't just look at it and go, yeah, cool, whatever. So you need to sit down and you might want to verify one of these identities yourself. Okay, so this would say that if I add two matrices and multiply it by a scalar, that's the same as multiplying both of them by the same scalar and then adding the matrices. So I could ask you a question like, what is that plus and what is that plus? Well, that's the plus of two matrices. So is that. So that's the same. I'm just saying, at the very least, you want to go through these and audit every part of the equation, left and right hand side, and make sure you know what it's talking about. What is everything? Is that an n vector? Is it a matrix? That kind of thing. Okay. Matrix norm. So like vectors, we have an idea of the size of a matrix, or if you like, the length or something like that. And it's going to be the sum of the squares of the entries of the matrix, and then the square root. So that's it. People also sometimes talk about the RMS value of a matrix, and that would be, in fact, the norm of A divided by square root mn, because mn is the number of entries here. And so that would be the RMS value of the entries of A. Actually, you don't hear people talking about that too much. Okay, now when A is a vector, we already have a definition of the norm, but fortunately in that case they agree completely, so that works. And this would have the same norm properties that norm of a vector had, right? That if you scale a matrix by a number and take the norm, it's the same as multiplying the absolute value by the norm, and so on. That's the triangle inequality, okay? and so on. These are basically analogous to the vector one, so we're not going to say anything about that. One cool thing is I now have a distance between two matrices. So I can have a distance between, which is very cool. So I could do something like this. I could have the rainfall at 10 locations over a year. And I'd represent it as a 10 by 365 matrix. We talked about that. So I could have a matrix A, which is the 2015 rainfall, and a matrix B, which is the 2014 rainfall matrix. They're probably not the same. I mean, that would be pretty weird if the exact same amount of rain fell on every single day of 2 years in these all 10 locations. That'd be crazy. But we can actually now talk about things like, in that case, I can have A minus B and take the norm of that. And that's going to give, that's something that tells me how close were the two seasons of rainfall. So at least we have a notion of a distance between two matrices then. One thing before we go on, and I'm not going to come back to this, but I should say, well, it's true for vectors as well. There are other norms of vectors than the one we look at, which is the square root of the sum of the squares. And there are other norms of a matrix other than the square root of the sum of the squares of the entries. But we're not going to use those in this book or this course, but you should know that there are other norms, and they're usually denoted by some kind of mnemonic. I'll just tell you one just for fun. So here's one. There's this thing, and that is actually the sum for over I and j of the absolute value of a, I, j. There you go. There we go. It's that. Okay? And so it's the sum of the absolute values of the entries. It's also clearly kind of a measure of a size. It does satisfy all these properties, right? But we're not going to be using that norm in this course. You may use it in other courses, in statistics, machine learning, other areas. You might end up using it. So just be aware that there are other norms, in which case the norm we're talking about here is called the Frobenius norm. That's named after a mathematician named Frobenius. But for here, it's just going to be it's just going to be the it's simply going to be, we're just going to call it the norm.